Hello, I'm Dr. Maurice Dupre, and in this section we're going to discuss differentiation rules. Remember, the derivative is actually a limit, and if we had to calculate a limit every time we needed to calculate a derivative, the process of dealing with differential calculus would be very slow. So it's the rules that enable us to calculate derivatives without having to calculate limits every time. Let's look at how this works. The definition of the derivative of f at x is f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. Notice this is a limit of the form 0 over 0, and those kind of limits are not limits we like to have to do. We can calculate them. We've known how to do those, but remember, it involves algebraic manipulations. Here, if I replace the h by 0, I have f of x minus f of x, which is 0, and replacing h by 0, I get 0. So this is a limit of the form 0 over 0 every time. So our differentiation rules allow us to break the differentiation problem into differentiating the constituent parts of the function as an algebraic expression, similar to the way we do with limit laws. Well, let's look. To begin, our first rule is very simple. The derivative of a constant function is simply 0. If f has the constant value f of x equals c, then the derivative df over dx, which is also denoted f prime of x, or d by dx of c, equals 0. Just quickly, let's look back at this definition for a minute. Notice if f of x is always c, then this is c minus c. The numerator in this limit becomes 0 every time, and so what we have is 0 over h, which is 0, and the limit of 0 is 0. And so consequently, the first rule is an easy consequence of the definition. Let's look at another rule. This is the rule that enables us to deal with powers. If n is a positive integer, then d by dx of x to the power n, that is the derivative of x to the n, is nx to the power n minus 1. Remember, the way this works in effect is the n is coming down front. The exponent comes down front, and then the exponent gets lowered by 1. So we take the original exponent, put it in front as a coefficient, and then get a new exponent by lowering the original exponent by 1. That's called the power rule. It actually works for every real number power, but to begin with, we'll only be applying it for positive integers and then negatives. Our next rule is the constant multiple rule. If u is a differentiable function of x and c is a constant, then the derivative with respect to x of c times u is c times du dx. So if I'm multiplying, if I have, for instance, differentiate 7 times u, that would be 7 times du dx. The fourth rule is the sum rule. So the fourth rule says, if u and v are differentiable functions of x, then their sum u plus v is differentiable at every point where u and v are both differentiable. At such points, d by dx of u plus v is du dx plus dv dx. What this is telling us is that if we have a sum of terms, we just differentiate each of the terms and then add the results corresponding. So consequently, combining this with our previous rule, the constant multiple rule, when I have a sum of terms with constants in front of the various terms, all I do is differentiate each of the individual terms and ignore the constants, letting them go along for the ride, sort of. So that's the sum rule. And finally, I'm going to skip to rule 7, which is the power rule for negative integers. If n is a negative integer and x is not 0, then the derivative with respect to x of x to the power n is nx to the n minus 1. Why is the requirement x not equal to 0 when n is negative? Well, notice if n is negative, x to the power n is actually 1 over x to a positive power, and so we can't have 0 in the denominator. So consequently, what the power rule for negative integers is saying is that the power rule still works even if the exponent is negative. So those are our basic rules, and so what's the bottom line on this so far? We differentiate terms, a sum of terms, term-wise. The constants stay in front of each term, and we basically can apply the power rule to powers if they are positive integers or negative integers. Now, what about for the power 0? What if we had x to the power 0? Well, x to the power 0 is 1, and remember our constant rule tells us that the derivative of a constant is 0, so that would say the derivative of x to the power 0 is 0. Well, what does this rule give us, the power rule, if n is actually 0? We would have 0 times x raised to a power, and 0 times anything is 0. So we can think of the case of the power rule in the case of a 0 for the exponent is still giving the correct answer. So now the power rule we can think of as works for all integers, positive, negative, or 0. Well, let's see how these basic differentiation rules simplify the process of computing a derivative. Here in this example, I have the function y equals 6x squared minus 10x minus 5 times x to the negative 2. And I doubt that you would like to try and calculate the derivative of this using the limit process. So let's do it with the rules. So dy over dx is equal to, remember our sum rules tell us we can just differentiate each term, but then when I go to the first term, it's a constant 6 times x squared. Our constant multiple rule tells us that's just the constant times the derivative of the expression. And then minus 10 times the derivative of the x, and minus 5 times the derivative of x to the negative 2. And now our power rule tells us the derivative of x squared is 2x. The derivative of x to the power 1 in effect is just 1. And so alternately 1 times x to the 0. Maybe I'll just write that for emphasis. 1 times x to the power 0 minus 5. And our power rule here tells us times negative 2x to the negative 3. And so we can simplify this. 6 times 2 is 12x minus, notice the derivative here that resulted x to the power 0 is just 1. Anything to the power 0 is 1. So we have just negative 10. Negative 5 times negative 2 is plus 10x to the negative 3. I'd like you to notice that when I look at the original expression, differentiating 6x squared, we can go directly from there to the 12x by simply taking that exponent 2 and multiplying by the coefficient 6 to get the 12, lower the exponent down to 1. We get as a result the 12x. The derivative of x is 1, so negative 10x has derivative negative 10. And then negative 2 times negative 5 is plus 10 times x raised to the power negative 2 minus 1 is negative 3. So when we're dealing with these sums of terms and we're dealing with powers and coefficients, one convenient thing to do to speed things up is apply the power rule in the form of taking the exponent and multiplying by the coefficient to get the new coefficient, and then just lower the exponent by 1. So for example, if I were to differentiate 7 times x to the 5th, what I would get in this case, 5 times 7 is 35, x, lowering the exponent by 1, the new exponent is 4. It just speeds things along. what we're doing is combining the power rule and the constant multiple rule when I do this. And of course, in general, then the sum rule tells us that if I have a bunch of terms of this form, we just do each term separately and combine them. Now let's look at the rules for dealing with products and quotients when we're trying to compute derivatives. Okay, rule number 5 is the derivative product rule. If u and v are differentiable at x, then so is their product u times v, and the derivative with respect to x of uv is equal to u dv dx plus v du dx. This rule looks a little strange by comparison to the normal rules, I guess you can notice. Here we don't have that the derivative of the product is the product of the derivatives, and it's extremely important to keep that in mind. It's a more complicated rule, and so basically one could say you could begin by differentiating the first factor, multiply by the second factor, then first factor times the derivative of the second, or you can simply begin by copying down the first factor, differentiating the second factor, plus now copy the second factor and differentiate the first factor. In any case, notice you've got two terms, and in each of those terms, one of the factors got differentiated and the other one did not. And together, each one gets differentiated one of the times. Here the v got differentiated, here the u got differentiated, here the u was not differentiated, here the v was not differentiated. Okay, so that's a little tricky. Now let's look at how we deal with quotients. For the quotient rule, it's even trickier. If u and v are differentiable at x, and if v at x is not equal to 0, then the quotient u over v is differentiable at x, and the derivative d over dx of u over v is equal to v du dx minus u dv dx, all divided by v squared. That is, begin by copying the denominator, then multiply by the derivative of the numerator, put a minus sign, then copy the numerator, and multiply by the derivative of the denominator. It looks sort of like the product rule, except in this case we have a negative sign instead of a plus sign for what we have in the numerator. But then finally in the end you have to divide the whole thing by the square of the denominator. Here we have down here v squared. Now, one thing to keep in mind is that if you get these two confused in a problem, you'll come out with the wrong sign, and that makes it completely wrong. So consequently, how do you remember which goes first? Well, the way to remember which goes first is that the numerator gets differentiated first. You see that? Differentiate the numerator first. In that first term with the plus sign, it's the numerator that got differentiated. The denominator just rides along as a factor. Then minus, now copy the numerator and differentiate the denominator. Okay, we've seen now how to differentiate products and quotients. The quotient rule is the trickiest, so let's look at an example where we have to apply the quotient rule. Here we want to differentiate the function y equal 2x plus 5 divided by 3x minus 2. So remember, for the quotient rule, we've got two terms in the numerator, and the first term is the derivative of the numerator multiplied by the denominator. What is the derivative of the numerator? Well, derivative of 2x is just 2, and the derivative of 5 is 0. So the derivative of the numerator is simply 2, and we multiply by the denominator. Then we put our negative sign, and now we copy the numerator and multiply by the derivative of the denominator. So now we just concentrate on the denominator itself. What's the derivative of that expression? Well, 3 times the derivative of x is 1, so the derivative of the first term is just 3. Derivative of the second term is 0 since the derivative of a constant is 0. So the derivative of the entire denominator is just 3. Now we divide by the square of the denominator. It's important to remember this last step of dividing by the square of the denominator. So there's our derivative applying the quotient rule, and of course I can easily see that this would be a nightmare to try and differentiate using the limit definition of the derivative. So I'm very glad I have a simple quotient rule which allows me to write down the derivative easily. Well, let's look at another problem where we use differentiation rules to differentiate. Okay, here I want to differentiate the function v equal 1 minus t quantity times the quantity 1 plus t squared, all raised to the power -1. At first, this looks like a product. If I try to apply the product rule, though, our rule so far will not tell us how to differentiate the second factor. In other words, if I said differentiate the expression 1 plus t squared to the -1, well, I don't have a rule for doing that directly because I've got a power function, and inside it I've got something other than just the variable. That means in order to differentiate, I effectively have to turn this into a quotient. The -1 power, remember, is 1 over. So the function I'm differentiating is really v equals 1 minus t divided by 1 plus t squared. Now, I can look at this as a product, but when I do, I would look at it this way: 1 minus t multiplied by 1 over 1 plus t squared. So now my second factor, you see, is a quotient where the numerator is just 1. The first factor is easy to differentiate. Let's apply the quotient rule directly to this. So dv dt is equal to, remember, begin by differentiating the numerator. Well, that's just -1. Multiply by the denominator, 1 plus t squared, put a negative sign, and now copy the numerator, 1 minus t, and multiply by the derivative of the denominator. Derivative of 1 is 0, derivative of t squared is 2t, and then what's our last step? Take the denominator, square it, and that becomes the new denominator. So there's our derivative. Now, if we had applied the product rule to do this, we would say the derivative of the first term, which is -1, times the second term, 1 over 1 plus t squared, plus the first term times the derivative of the second term, and then when I go to differentiate the second term, I'd have to apply the quotient rule to it. The derivative of the numerator is then 0 times the denominator, 1 plus t squared, and then minus the numerator times the derivative of the denominator, which is 2t, all divided by 1 plus t squared. Quantity squared. Close off the bracket, and there's our answer. Notice the 0 times all of this denominator is nothing, and so our numerator is effectively -2t. So here we have the -2t times the 1 minus t, which we had here, and the 1 plus t squared squared. But notice over here, we have -1 and only a 1 plus t squared. But if I put the common denominator, 1 plus t squared quantity squared, I'd have to put another 1 plus t squared up in the numerator here. That is, if I change this to 1 plus t squared there, then I have to square it down there. And now you see I could combine these two terms and have the same result. What I'm trying to get at here is that in many situations, there will be more than one route through these differentiation rules. And if you follow the rules correctly in two different routes, you will end up with expressions which don't necessarily look exactly alike, but in fact they can be rearranged to be the same. If they can't be rearranged to be the same, then in one of the routes at least you must have made a mistake. Well, the derivative of a function is again another function, so consequently we could differentiate that function. When we differentiate the derivative of a function, we call that the second derivative of the original function. Differentiating again, we get the third derivative, and so on. We call these derivatives of higher order. So let's work a problem where we find the derivatives of all orders for a function. Here I have the function y equal x to the fourth divided by 2 minus 3/2 x squared minus x. And we want to find the derivatives of all orders for this function. Now remember, when I divide by 2, that's the same as multiplying by a half. So this is treated just like a constant 1/2 in front of the x to the fourth. So to find dy dx, which we denote by y prime for short, we just get 4 times a half, which is 2x cubed minus 3/2 times 2 is 3, x to the power 1 minus the derivative of x is 1. So there's our first derivative. How about the second derivative? The second derivative, which is d over dx of dy dx, which is, notice there are two d's here, so that would be d squared y, and two dx's, so that's dx squared. That is, in reality, you can think of a parenthesis there, d squared y over dx quantity squared, but we don't usually write that parenthesis, so it's usually just written d squared y dx squared, also written as y double prime equals, well, differentiate again. 3 times 2 is 6, x squared minus 3. What about the third derivative? Y triple prime equals 2 times 6 is 12x, and the derivative of 3 is 0, so y triple prime is just 12x. What about the fourth derivative? Well, it's a little bit difficult to see all these primes. I'll write them this time, but we've got 4 primes there. The way this is written would be y with a little parenthesis around the 4. In other words, you write it as an exponent, but with a parenthesis around the exponent, and that indicates the order of differentiation. So our fourth derivative of y is the derivative of 12x, which is just 12. And so what's the fifth derivative? If I differentiate 12, what am I going to get? 0. Well, if I differentiate 0, I just get 0. So that means all the derivatives of orders 5 and above are 0. So all those derivatives of order n greater than or equal to 5 are 0. Let's look back at our original expression. What did we have there? We had a polynomial of degree 4. What we've really discovered here is that if you take a polynomial of degree 4, that all orders of derivatives beyond 5 are going to be identically 0. And you can easily see that that would happen no matter what the degree is. If you differentiate more times than the degree of your polynomial, you'll just get 0. For a polynomial of degree n, the derivatives of all orders greater than n are 0. Let's look at another problem where we apply the differentiation rules, but here we'll see that it's useful to simplify before we differentiate. At this time, why don't you pause the video and try this problem on your own. Here I want to differentiate the function y equal x cubed plus 7 over x. I could apply the quotient rule directly to this expression, but on the other hand, I can easily see that x cubed over x is just x squared, and then 7 over x is the same as 7x to the negative 1. So now we get y prime, or dy over dx, is simply 2x minus 7x to the negative 2. It's simply applying the power rule to each term. So that's very easy by comparison to having to apply the quotient rule. Now let's look at another problem where we find first and second derivatives, and again, simplification is going to help. Here I have the function w equals quantity 1 plus 3z over 3z multiplied by the quantity 3 minus z. Ostensibly, this looks like to differentiate, we'd have to apply the product rule, and then when differentiating the first factor, apply the quotient rule. Now, that wouldn't be too bad for computing the first derivative, but I would get a pretty messy expression, and then computing the second derivative would be a real mess. It doesn't mean you can't do it. It's just that you might suspect when you see something like this, it might be better to simplify first, especially because there's only a 3z in the denominator here. So if we go ahead and divide it in, notice we get, for our first term in the first factor, 1 over 3z, which we can write as 1/3 z to the negative 1. And then the second term is 3z over 3z, which is just 1. So that already is looking simpler. And now let's just go ahead and multiply those two factors together. The product of the first two will be simply 3 times 1/3 z minus 1. Z to the negative 1 is just z to the negative 1. And then the first times the last here is 1/3. Z to the negative 1 times negative z will be negative 1 times 1/3, so we just get negative 1/3. And 1 times the 3 is just 3, and then 1 times negative z is just negative z. And so notice how much we've simplified the expression. In fact, we just really have two terms which will survive the first derivative. In other words, w is z to the negative 1 minus 1/3 plus 3 minus z. And so that means w prime is negative 1 z to the negative 2 minus the derivative of z is 1, so negative 1. And now it's easy to compute the second derivative. Negative 2 times negative 1 is 2, z to the negative 3, and derivative of 1 is 0. And so that's all there is to the second derivative. So you can try this on your own using the product rule and the quotient rule in the first term, and you can see how messy the result will be, and then you can try to compute the second derivative as a good exercise and see if you can get it to reduce to simply 2z to the negative 3rd power, which it would have to do because the rules are consistent. Now we've seen how we can work differentiation problems with using the rules instead of the limit from the definition. It makes it much quicker to go directly from the function to its derivative function. And notice when you do this, it's useful to simplify first whenever you have to compute derivatives, especially if you have to compute higher derivatives. Also, if you're computing higher derivatives, it's best to simplify the derivative expression as much as possible before you go on to compute the second derivative and so on. That'll make the process easier. Keep in mind the rules are consistent. If you use two different routes through the rules to differentiate a function, you might obtain expressions which don't look the same, but you should be sure that if you've done it properly and correctly, they are algebraically equal. And so consequently, you can't go wrong even though the results look different.